the session forward.
Hello, everyone. This is Dr. Meela Mitra. On behalf of STEM&Space, let me welcome all of you to another very exciting session here today. So we have Dr. Dipankar Banerjee with us. Dr. Dipankar Banerjee is currently the director of the Aryabhatta Research Institute of Observational Sciences, in other words called ARIES, at Nainital. He is an astrophysicist with a bachelor's degree in physics from St. Xavier's College and a master's degree in theoretical physics from University of Kolkata. He has obtained his PhD from Indian Institute of Astrophysics and completed 2 postdoc tenures in reputed institutes in Europe. Dr. Banerjee's area of interest is the sun and the solar atmosphere. His work involves theoretical and numerical modeling using data from ground and space-based instruments. His work has enriched our understanding of the sun and its impact on space weather. He is the co-chair of the science working group of the Aditya mission. Aditya is the first dedicated Indian mission to study the sun, expected to be launched by ISRO around 2021. He's also the project coordinator for the National Large Solar Telescope Project, NLST, which is a proposed 2-meter ground-based telescope planned to be installed at a Himalayan site. He's also involved with NASA's Punch mission. He has more than 120 peer-reviewed publications with around 3,000 citations in international journals. He's currently supervising 6 PhD students, while 11 have completed their PhDs. Apart from his scientific career, he also has interest in various other activities. He's trained in Hindustani vocal and is part of a Bengali theater group, Sharannik, and regularly performs in plays, participating in national and international theater festivals. Dr. Banerjee's love for science and zest for life are infectious. So with that, we're so excited to host you here today.
Yeah, let me just try to share my screen and ensure that all the technicalities are addressed.
Yeah, that's good. We can see it. And we are all excited to hear about the Aditya L1 mission. So,
do you see the full screen, just to confirm?
Yes, I do see it.
All right. Okay. Thank you very much, Mila. It's a pleasure for me to be on your platform. I hope through this virtual mode, we are able to reach to some extent to the younger minds, because I always like to, meet
There is some network issue from Dr. Dipankar's end, I believe.
Okay, yeah. So
we will get back to him as soon as Dr. Dipankar is back.
Right.
So in the meantime, students, I would like to tell you, like, as a part of basically this engagement, you guys are free to ask your questions in the chat. We will bring all your questions to Dr. Dipankar at the end. But if you ask some very relevant questions, we'll be bringing to Dr. Banerjee in between as well, so that he can address it while he's giving his speech. So yeah, and yes. So basically in this session, Dr. Dipankar will mostly be talking about the Aditya L1 mission. And we are glad to share that Dr. Dipankar is actually working on this mission as the one of the scientists. So yeah, Mila.
Yeah. So Aditya L1 mission. So as you'll find out, Aditya means the sun. And Dr. Dipankar Banerjee is one of the scientists working on that. So we are back with Dr. Banerjee. Yeah.
Sir, you are muted.
Yeah. Are you able to hear me now?
Yeah, we can.
Yes.
Okay. And the screen is also visible, right?
Yeah, that's fine.
Okay. Okay. Yeah. Sorry about the technical.
Yeah, no problem.
fault.
That's part of the
So,
online world.
okay. Okay.
Yes.
So, so as I was mentioning that, I'm just sharing with you some pictures of the, observatories what we have in this country. So this Himalayan Chandra telescope is situated in a location called Hanle, about 200 kilometers from Leh. This is, my parent institution, Indian Institute of Astrophysics, Bangalore, who operates this telescope remotely from Bangalore through a dedicated satellite link. And we also have one of our oldest 2.34 meter telescope at Kavalur near Jolapeta in Tamil Nadu. But more recently, I moved into this new institute called Aryabhatta Research Institute, where we have cutting edge facilities in terms of the largest optical telescope from this part of India, and also atmospheric sciences. So very briefly, I'm just mentioning where I am in case students who are interested to visit us and get to know a little more about it. You are most welcome to come and visit me. This is a place where I am. I'm sitting in this particular place now. We are 10 kilometers south of Nainital city. But more recently, we have a new campus, a place called Devasthal in Mukteshwar, which is 50 kilometers east of Nainital city. And this is hosting the largest nighttime telescope from this part of the globe. So that's actually nation's pride. This is a close-up of this building where I am. It's a beautiful place. You could see the plains 2 kilometers down below. And I'm sitting in this room now here. This is the window where you can peep in and see me here. So there are different, obviously, facilities here. We have students' hostel, auditoriums. We have several labs here in terms of optics lab and electronics labs and so on. We also host a 40-inch telescope, which is one of the oldest from this country, actually, which is still operational. And on our PhD students, once the sun sets in an hour or two, they will walk up to the hills and will start their observations from there as well. So this is a different life. And I hope some of you get excited to participate in this kind of career also in future. So I'm just giving you some excitement, I hope, so that you take up this as your future career.
So one question I have is, it is open to the public?
Of course, it is open to the public. What happens is we have open days, and typically because of the pandemic, we had to close down most of these things. We do have a visitor center and science center as well. So there we have a even small planetarium, which can host about 30, 40 people. And we have, small shows. So primarily we cater to the students with prior appointments. And again, it has started. So yesterday only, St. Joseph School, 20 odd students. So we are taking smaller group in number now. So 20 odd people, they visited us. We arranged for certain interaction session and so on. So, and the nighttime, observations is more with a prior appointment, so to say, in small groups and so on. And we are opening up again, I would say that way. So there is also a solar telescope, 15 centimeter, which looks at, primarily at the solar atmosphere and the flares and so on, which I will be talking about. And we also have a 50 centimeter Smith telescope. Incidentally, it has a very large field of view, so it can look at a large portion of the sky, and we are planning to use it for some other, space awareness programs and all that as well. This is a close-up of this 1 meter telescope, which I was saying it's a, was inaugurated in 1972, but still fully functional, more than 50 years. It has given 50 odd PhDs already. Almost every year there is one PhD which is coming out of this telescope, even today. This is a close-up of that 15 centimeter H-alpha solar telescope, which I was referring to. And that can be, of course, observed in the daytime as well. We, at Devasthal, which is, as I mentioned, 60 kilometers from Nainital, we have another smaller telescope. What happened was, about 10 years back, when we identified the site, it was important to sort of, start some operations in the site. So we bought a smaller telescope. It's a DFM telescope, and that's again fully functional, and a lot of students do work for their PhD from this, because this is a very robust, good telescope with a good amount of, optics and, imaging quality cameras and all that. Of course, this is the nation's pride now, 3.6 meter Wavell optical telescope, and it has many. We are also bringing up a new facility, which is called a 4-meter class liquid mirror telescope. It's quite an interesting thing that, instead of using glass mirrors as a primary mirror, you use mercury, put it in a bowl and rotate it in a very faster speed. So the mercury will spill and will create like a plate, and that becomes a reflecting surface. The idea is that, of course, this is, much cheaper than a traditional conventional telescope, and much more compact and all that. So you could achieve a very large, primary mirror, even with, much less cost. But on disadvantages, it's only looking at the zenith. You cannot really, move the telescope this way or that way. So, but this will be used for a lot of transient studies, anything passing within the field of view. Even if there is a satellite passing or a space debris passing, we'll be doing that. And a lot of automation will be there, completely with AI/ML applications and so on. We will be used. I mean, all the students must be very much familiar with these terminologies now: artificial intelligence, machine learning. So these are direct applications of these kind of large volume of data handling with a good number of students. And you can do it from anywhere, because the data will be collected almost like a robotic mode, and the data can be distributed to anywhere where students are sitting, and they can do their own piece of software development and try to identify an object from this large volume of data. So these are very promising things which are coming up. This is the close-up of this 1.3 meter telescope. Of course, you can see the beautiful Himalayas. You name any mountain, a peak, Nanda Devi, Nanda Kot, Trishul, you all see it on a regular basis from there itself. It's again a sort of pleasure to be there. This is the liquid mirror telescope which I was talking about. I'm rushing through this slide just to give you a glimpse of what all facilities we have at ARIES. This is the largest 3.6 meter telescope which I was referring to, and as you can see, this is the dome. It's a big structure. It's a huge achievement for us now. So today's area, or today's talk, and as Mila mentioned, that my subject is the only tiny sun in this entire universe, but this is our nearest star, and we can study the sun with much better precisions now because of large development in terms of the ground-based and space platform. So we have n number of satellites looking at the sun all the time with so many eyes, with so many goggles and so on. Because when we say goggles, means you look at different wavelengths and then you see the same object differently, and that's how astronomy is actually growing. So this is called actually multi-wavelength astronomy, and sun is actually the ideal platform for that. So sun, like all stars, is a dynamic star, always active, always changing. The more we learn about it, the more we learn about all stars. So that's again another very important element. Why do we have to focus so much on the sun? Is the amount of details what we learn, which can learn from sun, is almost impossible to be explored for other astrophysical objects or stars. So one can always extrapolate the knowledge what you get from studying the sun to other stellar objects that way. So this is a movie I'm showing, taken from a NASA satellite called Solar Dynamic Observatory, and it is looking at a particular heights of the atmosphere of the sun. And as you can see in the sun, you have certain region where it is very bright, and there are certain region which is comparatively darker. So these regions where it is bright, they are called active regions. And now we understand in those regions, there are strong presence of magnetic field. Basically, there are certain things called sunspots. These are dark, spots on the surface of the sun. And now we know that these dark spots actually are regions where strong magnetic fields are concentrated, and they are all the time changing. So magnetic field is not there everywhere all the time. So there are certain places where these magnetic field concentrations come up, and then they evolve with time. So here you see this example that some amount of material was confined within these region because of these kind of structures, which are looked like this kind of loop-like structures, right? They are nothing but called magnetic field lines. If you have done some experiments in the school with the, say, bar magnet, you know, the magnetic field line starts from, the North Pole and gets to the South Pole. It's like an imaginary topological, a representation of the magnetic field environment in and around a bar magnet. So similarly here around the sunspot, we now see that the material is, somehow structured in a three-dimensional way through these kind of loop structures. But now these loop structures at some point of time can explode. So why it will explode? Of course, we need to understand why it is stable at certain point of time, and then why it is exploding. And when it is exploding, what we are seeing from this movie is huge amount of material which was confined within these large loop kind of structures are expelled into the interplanetary space. Now, if these material move through the interplanetary space and eventually reach Earth or Earth's atmosphere, then there could be a devastating effects. And obviously now what we are also very much concerned is we have our near Earth environment is completely filled with n number of satellites and other real estate, so to say. So these satellites can get badly damaged by these kind of huge material. What you see is ejected from the sun and then impacts with that. So in general, now what we understand in the sun, there are certain regions which are called active regions, where underneath you find strong magnetic field called sunspots, and there are certain regions where comparatively quiet, but nothing is quiet in the sun. You will see there is always something is happening actually of different time scales here as well. Sun is a normal star. It's a middle-aged star, main sequence of spectral type. You don't have to worry about these jargons. You may or may not have that background, but just be aware that we all are born from certain way, and then we go under evolution, and then we die. So sun also as a star is born from the interstellar medium, and then it goes through its middle life, and then it becomes old, it becomes a red giant, and eventually it will die. So we don't have to worry about this is going to still be in this middle age for another million years, and we will have no problem in our lifetime. So it's a spatial star because it is the only star which we can resolve the spatial scale on which fundamental processes takes place. So I told already that most of the objects in the sky, we normally study them as a point object. We really cannot see the details on the surface of that object. Whereas sun being slightly closer to us, we are now able to see such great details. As you have seen from the previous slide and the movie, that how much details we can see from the sun, which is not possible to be seen for any other almost astrophysical objects, apart from few planets. I mean, they are in our own system. The sun is also a special star because it provides almost all the energy to the Earth. Our existence is because of the presence of the sun at an appropriate distance away also. From a physics point of view, actually, it provides us with a unique laboratory to learn about various branches of physics. I mean, from my introduction, you have probably learned that, I was a student of physics up to my master's level. So I only studied, classical physics, atomic physics, nuclear physics, solid state physics, condensed matter, which is called these days. These are all basic subjects of physics. So sun provides an ideal laboratory to verify certain branches of physics which I have already named, whether you call it nuclear physics, whether you call particle physics, call atomic physics, you will find some application from the observations of the sun or physical models of the sun or numericals from the sun and so on. So that's how I got mostly attracted towards study of the sun, because of my background in physics. So if there are physics students, I can spend a full day to explain how many different branches are there which you can study in the sun. So in the sun, actually what happens is, right in the core we have these thermonuclear reactions that are happening where the energy is radiated. I will not go into too much of details, but then energy is propagated through radiative process. Energy can be propagated by radiation, convection and conduction and so on and so forth, right? So in this 30% inside the sun, energy is transported through radiation, and this last 30% inside the sun, the energy is propagated through convection. It's like a big bowl of soup bowl, and then whatever is happening in the interior somewhere here, they come up. And that's how actually the magnetic field also is generated somewhere at the base of this convection zone. This is called the convection zone. You can compare with your bottom of your pot, and then if you boil that pot, you will know that if you have some noodles in the soup, the noodle starts or the small little spaghettis, they will try to float at the top of the bowl. So this is what happens in the case of the sun as well. So these magnetic flux tubes, they're like rubber tubes. You can also mimic it that way. The rubber tube will try to come up to the surface here, and they will form these sunspots. So these are called actually the dark regions on the surface of the sun. They're called sunspots. So the different layers in the atmosphere of the sun also has been depicted here. I will come very slowly into that. As in Earth, you have a question?
Oh, yeah, sorry. Yeah, sure. So basically the students have been asking many questions. So I found a few relevant ones basically. Yeah. So one student was asking about the sun telescope that when you were talking about. Like we have a 1.5 meter, 15 centimeter solar telescope. Okay. So basically the question is like, why did they decide that there should be 15 centimeter only? Like, did we decide to build any bigger or smaller? So like that was one question. And the second one was, when we were talking about the solar flares and all. So student got very concerned, and one of them asked that, sir, what damage can a solar flare cause? And how frequent do you think it is? Right. So
both are very, very good question. So the first one, I should have probably explained it a little better, that the size when we say it is a 15 centimeter or a 1 meter is basically the diameter of the mirror. These are actually, you see, if you have a very small telescope, you can also have a small little lens, and then your parallel rays will be converging to a focal point, and then you can image that distant object by a lens. But bigger the lens you make, it's actually harder to make that lens, and there are also other optical errors which comes of construction of a bigger lens. So in a way, modern day, most of the telescope which are of reasonable size for professional science or astronomy, it's all made of mirrors. So the diameter of the mirror, now the question is why one should go for bigger mirror. So as you can imagine, bigger you have the basket, you collect more more photons from the space, right? So what we are trying to do is, we have a big mirror, and it is looking at the sky, and from the sky, this distant object, it is emitting certain number of photons. So if you have a small bucket, it will only collect a few photons. If you have a bigger bucket, it will collect many more photons. So the idea is, now as big as is possible. Now then there is a limitation. Question comes, how big the mirror you can make. Mirror has to be stable. Of course, it will be more expensive also. 15 centimeter is very cheap to make, but when you make a 4 meter, it will cost you a few hundred crores. So that's how it becomes more and more. Since you asked the question, actually nowadays what people are doing is, they're making 100 mirrors, and they're putting those small say 1.6 meters side by side, and effective diameter then becomes a 30 meter. In fact, there is a project where India is involved. This is called a 30-meter telescope project, which is expected to be in Hawaii. This international project that's going to be one of the largest, telescope in the globe, and that is with that kind of concept that you have many 1.5 meter size mirror, and then you keep it next to each other, and then collect all the light together and make a effective 30-meter kind of thing. That was the first answer of your first question. The second one is about the flare. I will come actually a little more details, but let me get a slight answer to that. So flares can happen, many flares in a day to few in a month also. That depends on how many sunspots you will have on the surface of the sun. And now we understand that these number of sunspots on the sun also varies with time. In fact, there is something called a solar cycle. Some days you will find there are many sunspots, some days you will find there are no sunspots at all. And that number change variation happens in a time scale of 11 years. So there is a certain period where you will find many sunspots. So that means there could be possibility of many flares. And again, how many sunspots are there in the proximity, how complex this active region is, all those factors actually makes it that the flare will be how severe. There are different sizes of the flares, different scales of the flare. We call it X class, M class, classifications are that based on the, how much energy actually the flare will emit. And based on that severity of the flare, that can damage these satellites. Definitely, it can damage our, even in our neighborhood, we have a lot of electrical systems. We have transformers and so on. So it will impact with that. If you are planning to go in space for a spacewalk and all that, you can be affected. These days, people are talking about, space explorations or a sort of a little trip to moon. So obviously, when you go to the moon, you will be affected by the solar flare actually, because the Earth's magnetic field is not there to protect you there. So, so again, coming back to your answer, many flares can be in a day, depending on how many sunspots are there, and depending on how much complex the sunspot active regions are, the severity of the flares will be there.
Yeah,
okay, should I move on?
Yeah. Yes, please.
Yeah, it's good. I like a little bit of interaction. So when you have on a live platform, it becomes much easier. So it doesn't matter, if I don't cover many slides, it doesn't matter. So you feel free to stop me at an appropriate time, and we will continue, maybe another session. Sir. So I like, this way of. So this is what actually I was referring to. The sunspot was discovered by Galileo more than 400 years back. In fact, when we do science, it's also actually quite important to know the history of science. Because science is, very closely linked with the philosophy as well. And the way the society evolved, the way we have learned about the science, and how the, understanding about our universe, whether we are in the center of the universe or sun is in the, we are going around the sun, or the planets are going around the earth. So this kind of, debate was there way back before Galileo's time. And Galileo was one of the scientists who has actually suffered, because he was advocator of this concept that, we are revolving around the sun. Sun is in the center of our system. So anyway, so Galileo actually discovered these objects which are called sunspots, and Galileo also discovered, so these sunspots, if I now actually look at a more of a modern image, for some reason this movie is having difficulty, otherwise we'd have got a slightly closer view of this. Sometimes the zoom, the transfer rate makes a little difference. So these are like sunspot, as I said, are magnetic structures that emerge from beneath the surface of the sun. So this is always a pair of sunspots, and they are connected by these kind of magnetic tubes. And when these magnetic tubes, you can also think it in terms of, like rubber bands. So if you play around with rubber band, sometimes you try to twist this rubber band, and you know that beyond certain number of turns, these rubber band will snap. So here, these loop structures also have the same similar properties, that when these lines are tangled and break apart, they are creator of the solar storm. So this is what is related to the solar flares or coronal mass ejection. I will briefly explain what it is. But essentially, everything is coming from the magnetic field, and magnetic fields are concentrated regions, and they are connected by these kind of structures, and these structures, when they become unstable, then these kind of storms and all that happens. So the sun rotates every 27 days or so. I think I have to skip few slides, so let me because I will skip a few ones, otherwise I will not be able to cover. So essentially, I just wanted to briefly mention that any objects, apart from it is rotating around a central object, it also rotates around its own axis also. The sun also does that, and that makes this convection to be more effective, and then the generation of the magnetic field and all that is somewhat related with the rotation. Now let me come to the atmosphere of the sun. Normally, this is plotted here is the height, and this is the temperature here. So as you come from the surface of the sun to the atmosphere, temperature normally drops. That is what you expect. Even in Earth's atmosphere, if you come from Delhi to Nainital, you find it a little cooler because all your energy source is actually on the surface or interior in the case of the sun. But an interesting thing happens when I go further in the higher altitudes of the sun. The temperature actually rises, and from tens of thousands of Kelvin, it reaches almost up to millions of Kelvin. This is normal physics cannot explain. Normal physics, whatever thermodynamics and all that you study in your school, will not be able to explain this. So this is very, very peculiar in the case of the sun. And we know that the atmosphere of the sun is much, much, hotter than the surface. So these different layers have different names. So these are called chromosphere. Up to 2000 kilometers from the surface of the sun is called chromosphere. Chromo means color. Actually, during the eclipses, people observed certain colors in the second contact and so on, and that's how they named it as a chromosphere. And during the totality, when the solar disk is completely covered by the moon, you see the outermost atmosphere of the sun, which is called the corona. This is the corona, not the virus.
Another one.
Incidentally, the name of the virus has come from the solar coronal image only, because the solar coronal image from the eclipses look very similar to these, helmets and those kind of structure of the virus. So that's how the name has emerged from a different context.
And so basically, even when I'm to explain the student what is corona. So one thing I tell them is that while you were kids and you used to make the landscape with the sun, the spikes of the sun which you used to make was actually represent the corona of the sun.
That's correct. Because when you block the solar disk, because essentially in our day-to-day basis, we see the solar disk light, because that's very bright. And the emission from these atmosphere, of course, the other reason is they're very, a very thin atmosphere. So the density is very, very low. And so the emission is actually 1 millionth time than the solar disk light. So unless you block the solar disk light completely, you will not be able to see the very weak emission which is coming from the outer atmosphere. And that has these, spiky structures at certain places. I will show you some eclipse images, hopefully, by the end of the talk. So the different layers, what we do is, I mentioned in the beginning that we look at through different goggles. Essentially, different goggles allows you to look at different wavelengths. And here we do the same thing in the case of the sun. When we look at different filters, we look at different layers of the sun. So this is called the lower chromosphere. Same region. If we go slightly higher up, say about 1500, 1600 kilometers from the surface of the sun, the structure looks very different, right? It is the same region in the sun, right? So these are the sunspot pair. And when we go to a slightly higher height, we see more filamentary structures, and so on. So this is a filter called H-alpha filter. Incidentally, the same filter is there at Nainital in our telescope as well. So we look at most dynamics and flare studies and all that from this H-alpha. And if I go to several thousand kilometers above, and now we know that this temperature, lower and lower temperature means, actually it emits shorter and shorter wavelength. So the earlier images were mostly from extreme ultraviolet, and this image is taken from X-ray. This is from a Japanese satellite called Yoko, and then you could see the corona. These are very old pictures, but I just still have these things, that how structured these regions are. So these are the two sunspot pairs, what you were seeing earlier. So the same region here, here and here, but we have much more extended. This loop kind of structure is what I was referring to earlier as well, is seen in the X-rays as well. So what I have mentioned, that all these regions where there is a presence of magnetic field, how the magnetic field is connected by these different magnetic field line structures dictates about the evolution of that region as well. So here we know that active regions, what we were referring to, where sunspots are there, the magnetic field lines are more closed, like. And if I go to the polar side, where emissions are much, much weaker, you see, the things are much brighter here. This is much weaker here. These are called actually coronal holes. In the hole means, it's like a gap almost, and things can escape from that. We now know that the magnetic field lines are more open. You can see that it's like an open channel for particles to escape. So this particular slide and these are actually mathematical construction, that we do not have a direct observation that the magnetic field is exactly like this. But from our understanding of the physics, mathematics, and observation, we now can infer that probably the magnetic field lines are structured like this. And that matches fairly well with our observations as well. If I now look at, in the case of the Earth, this is, that that's rotation and the axis, and the magnetic axis also has a tilt and so on. But in the case of Sun, you see this is again a mathematician's reconstruction of the structure of the magnetic field. So in order to understand the dynamics and activity of the sun, we need measurements and theory of its magnetic field. So this is a crucial element. I just wanted to give you a flavor a little bit about why, solar physics is so important, because understanding the magnetic field and its evolution, it's done in the terrestrial environment, in the field of the plasma physics and so on and so forth. But there are a lot of, practical challenges in doing plasma physics experiments. Whereas in sun, it provides an ideal laboratory to do these kind of, experiments as well. And we see, we still do not understand many different things in the sun on that. So if I now compare with a mathematician's model and compare with my observations from extreme ultraviolet, they look pretty similar, right? So this is just an image of these coronal loops. And this is our mathematician who has done this modeling. So I just also wanted to impress on you how different branches of physics and different expertise, whether you do mathematics, whether you do computer simulations, whether you do observational science, or you do computer programming, all these skill sets are important to be collated to get a full understanding of the subject. So this is again another just a sort of classical example, I would say, this. So flares are quick, intense, but smaller explosions than CME. I will come to CME soon. They appear as bright flashes, sometimes followed by a burst of high energy particles that can travel. So here there is a flare here happening, and we are seeing this in a 304, one particular goggles, you can say. So you saw that there was a flare here and some material was ejected. Large flares can occur several times a year when the sun is nearly its peak activity. So this is the answer to one of the questions which you have asked later on. But large means, really, really with lots of energy, which can directly impact our satellite systems and our, power systems and so on. The snow in the clip is radiation from the storm hitting the spacecraft. So here also there were some movies here. So I'm just rushing a little bit. So here you will see that when we look at different filters, we can look at different aspects of these flares. So if you want to study the flare, you also need to study it at a different wavelength. and then you will be able to get more properties of these ejecta, which is coming out from the sun. Then CMEs are large solar storms. Large solar storms that can blast out a clouds of billions of tons of particles at over 2 million kilometers per hour. Smaller ones can occur almost any day. As again, it's a related question with your flare thing. As you see here, in fact, this particular guy, they just became unstable, and then the large volume of material they have thrown out. These material, which is almost like a form of a cloud, can reach Earth's orbit in 1 to 3 days. But only a few of them actually head our way, because the sun is a 3D space. So, these cloud can travel in all 3D directions, but only few will come towards us. But you can see that these guys, if they come towards us, we have to be a little cautious to protect the satellites. In fact, there are many commercial satellites which gets damaged completely by these solar storms and CMEs. Now, this portion of the movie is showing those structures with the coronagraph instrument. So coronagraph is mimicking a total solar eclipse, and we are able to now see the outer part of these ejectors. So now you see these ejecta, how big they could be, and if they travel towards us and we are somewhere here, it's not a very pleasant scenario here. So, but good thing is that we have plenty of satellites looking at the sun, so we can probably tell precisely when such explosion will happen, and if it happens, then what kind of speed with which the CMEs are coming towards us, and then we can probably try to protect some of these assets now. So this is what is a new field called space weather. Very briefly now, last 5 minutes or so, I will talk about our own mission called Aditya. I just put in the context of this. Aditya is our dedicated solar mission. It's a multi-institutional project. There are 7 payloads, and this is the complete list. You don't have to worry about too much because there are a lot of technical details of this, but you can just try to remember that there is a coronagraph which will look at 3 optical channel and 1 infrared channel. As I mentioned in my first part, that multi-wavelength astronomy is very, very important to look at different plasma at different heights in the atmosphere, and how you can characterize how much energy is there, and so on. So this coronagraph is being built at Bangalore at this point of time. It's getting assembled in one of our laboratories in Hosakote. Then we have the solar ultraviolet imaging telescope. This is near UV telescope, and then this is being built at Ayuka in Pune. Then we have 2 particle detectors. The particle detectors essentially looks at the properties of these particles which are coming from the sun, their nature, their charge state, their magnetic properties, and so on. We have 2 X-ray instrument which looks at different energies to study different kinds of flares. So this SOLEX, low energy X-ray spectrometer, will look at low energy flares, which is happening most of the times, and this high energy X-ray spectrometer will look at the high energy which are directly related to the big flares. So these are again built at different centers of ISRO and PRL and so on. We have a magnetometer which is also looking at the magnetic properties of these charged particles as it comes from the sun. So this is how it looks like. Here we have the big elephant, the coronagraph at the top deck. Then we have this imaging telescope, and then all these smaller other instruments are sitting at different parts of these satellite. And of course, this is the scout view. And then once it goes to the destination, we are going to a position called Lagrangian one. I'm not going into too much details, but it is actually a very, very interesting, again, location where we are reaching up about 127,000 kilometers away from the Earth. And it's only the ESA, European Space Agency, and the NASA, American Space Agency has been able to reach that far. So this is going to be a very, very big challenging thing for ISRO as well, to go that far for the study of the sun. In fact, after the Mangalyaan mission, we have been very adventurous, and we are looking at new destinations rather than just, launching another small satellite and going into the low Earth orbit and so on. So the very exciting time ahead. This is sun. If there is something coming out of the sun, as you can see, it travels through the solar corona, then in the heliosphere, and then the near Earth environment. So here it is our Earth. So point is that we need actually to really follow these structures with multiple instruments and many more eyes and minds and people. So I think we need a huge amount of manpower to study one CME, one flare, all the way as it comes from the sun and goes all the way through the solar corona to the inner heliosphere to the Earth. Because different kind of expertise are required to study this near Earth environment, heliospheric environment, and the solar environment as well. This is again another classic example that how different branches of astronomy, geophysics, atmospheric sciences, all these things are getting coupled for a complete understanding of the subject. So I think the future is very, very bright. This is the coronal image, what we mentioned earlier. This is a solar eclipse image taken at different times, 2006, 2008, 2009, 2010. So as you see here, that the structure, and as it was mentioned here, you have this kind of helmet-like structure. You have these spikes. These are called polar plumes and all that. This image, incidentally, has been also taken with two different goggles, two different filters, and we are overlapping these two images, one in red and one in green, to show that there are probably different plasma elements corresponding to different filtered images, because they don't always overlap. See, the certain features you see in red, certain features you see green. That means the temperature of these guys and these guys are different. So all these kind of different things we can study. Also, what you notice here, that the solar corona itself is varying with time. Every year they look very different, and this is all because of the presence of the magnetic field. How the magnetic field is structured in the 3D space. In fact, that is what is happening in my colleagues in Kolkata, Dipendu and his students. They do this kind of modeling. This was a prediction model. Again, you see how a physicist, a mathematician, and a numerical simulation guy, how they have predicted the eclipse one day before, how the eclipse image should look like from our understanding of the today's, say, few days before magnetic field positions and the atmospheric conditions and so on and so forth. So what is the magnetic structure of the corona on very large scale? How does the magnetic field change on a global scale with different time scales? All these kind of things we study. I'm sorry, this is slightly in technical, but yes. I just wanted to give a flavor that how different kind of advanced things are happening.
Actually, yes.
Yeah.
So sorry to interrupt, sir, but some of the students are actually interested in the other question about Aditya. Like different students have asked the similar questions. I will read those questions to you. Like one of the students asked that how will the Aditya rocket go to the sun without burning? And second student asked that how will the Aditya L1 reach the sun if there is so much heat? I think they should design.
Sir, and also about the material. So yeah, yes. How does it achieve that?
Okay.
Is a good question. Like Parker solar telescope.
So I should have a cartoon diagram already. I mean, if I had a blackboard, probably I would have done that. But essentially, we are going only 1% of the distance between the sun and the Earth. If the distance to the sun is of 100 unit, 127,000 kilometers is only 1 unit. So we are not really going that close to the sun. Having said that, there is actually a NASA mission called Parker Solar Probe, which is attempting to go much, much closer to the sun. But still it is, not, it has a different trajectory and so on. But it will go almost, 30% close to the sun. But for that mission, it is never going to look at the sun. As you rightly pointed out, sun is so bright, and so all the instruments, they will be looking away from the sun, on the Parker Solar Probe. But as far as our Aditya mission is concerned, we are much, much away from the sun. But I think a related question which Mila prompted is about the particle, what you said. That's actually important thing which you said. that if we go 127,000 kilometers away from the sun and from the Earth, we are away from the Earth's magnetic field. Actually, I did not talk about it much today. Earth has its own magnetic field, and that actually protects us from these, huge amount of particles and all that is coming from the sun. But once you go out of this shield, which is called the magnetosphere, then you are completely exposed. So these, satellite instruments are going to be bombarded with these particles. So it is true that when we are designing these instruments, we have to, make those instruments which are capable of taking these bombarded particles. In fact, these instruments are taken to the labs, and TIFR has such a facility where you bombard them with the highly charged particles and see whether the instruments can survive or not. So this is a part of the selection of the instrument components and things like that. Yeah.
So much for the answers.
Yeah. So I'm actually done. So I just wanted to, my last comment was that the future of solar physics in India lies with these young minds. These are some of my PhD students here, and we hold regularly workshops and so on. This was one last held at Leh. But I just wanted to also mention that now Aditya is expected to be launched next year because of the pandemic. Things have got largely delayed, but hopefully we will be launching it next year. And at ARIES, we are going to have the Aditya User Center. So I will be actually conducting very regularly more training programs. So we will launch the website also very, very soon. And there will be, periodical online, lectures and also in-person sessions. We will host these, students at different levels for making them, familiar with what kind of data Aditya will give, what kind of science problems one can think of. So there will be regular, student interaction. So this is called the Aditya, User Center support cell, so to say. If you want to use Aditya mission for certain observation, how you want to write a science proposal. So those exercises will be also taken up by Aditya support cell, and that will be in, at ARIES in Nainital.
Okay.
So I'm ready to take questions now. Yeah.
All right. Great, sir. So yeah, so I'll be taking a few questions to you. Like one of the students is interested about the Aditya L1 as a mission. So one student asked, "Sir, what is the L1 in Aditya L1 over here?"
Okay.
Right. So
yeah. Again, I did not explain it very much.
Yes.
So
Yes.
Lagrangian 1 point is actually a comparatively stable point. I do not have the cartoon here actually. So where what happens is, if once you are able to reach there, the force between the satellite and Earth roughly balances the force between the satellite and the sun. Of course, sun is much heavier object. That's why I said it's almost 99 unit away, but still the force is substantial, and we are only 1% away. So that once you reach Lagrangian 1 point, you can look at the sun almost continuously for much longer period. So it's in a 3-body system, there are actually 5 Lagrangian 1 points. So if you calculate the mathematically in a 3D space, what are the stable points for a 3-body rotating system, then you will find 5 Lagrangian 1 points, and we are going to Lagrangian 1 point. I don't have the cartoon, but if you just give a Google search, you will find Lagrangian points. There are 5 locations, and we are going to L1, which is in the Sun-Earth line, and that will allow us to look at more continuously towards Sun, and it will also require less amount of fuel to stay there for longer period of time. So that's again another big advantage. There is a NASA mission called Solar and Heliospheric Observatory SOHO, which reached Lagrangian 1 point in 1995, and it is still alive. So it's more than 20 years, we are looking at the sun continuously. So that's fantastic. I mean, we hope we'll be able to stay there for a long period as well.
Yeah, hopefully, sir.
So we have a few questions. Several people have asked about, will the spacecraft be made of special material because it will go so close towards the sun.
Yeah. So as I mentioned, that we are not going really close to the sun, so it is still very much part away from the sun. So majority of the other satellite, whatever components, you see, the particle hazard will be there because we are going away from the magnetosphere. But thermal wise, there won't be something specific. But when a solar mission happens, or sort of, we demand certain specification, we have to look at the sun, and we have demanded a very good pointing accuracy. That means, we don't want to go there and do any, sort of shaking and so on and so forth. That demands certain extra thing for the material what you choose. Why I'm mentioning this, a normal a sort of commercial satellite or even a communication satellite will not have such demands of precision of its pointing, stability, and things like that. So for a science mission, these kind of things are much more demanded. For that purpose, there has to be better thermal property balance and so on and so forth. So obviously some special materials or tested material has to be chosen as compared to say a communication satellite. So that way there are certain specific areas has to be chosen. Yeah.
So another question that I have, so one of the students is interested in knowing that are there any problem faced while making the Aditya L1? And like,
I mean, if I...
It is a very vast question, actually. Yes,
Right.
yes, that is the whole point.
I mean, including the pandemic also. But
yeah. I mean, any mission of this stature, where probably about 1,000 people are at least actively working from different aspects, from an engineering side, from satellite side, from instrument calibration side, from a science perspective, from the data transmission perspective. So there are challenges in every aspect. Every aspect there are challenges, because these science missions are also something which we are doing for the first time. We have never done before. That is the difference between a sort of another communication satellite and our kind of mission, because everything is first time. Yes. So obviously what you anticipate and what you design from say in a computer or from your standard knowledge, when you assemble that instrument and then make certain tests in the laboratory before you fly, because there is no choice of failure, right? Once it goes there, there's no point, there's possibility of any corrections. So that way there are obviously several challenges or limitations we face, and one has to also make certain corrections, certain adjustment, modifications. So it's a sort of ongoing continuous process, you can say. And as I think Mila mentioned, that pandemic has been very, very, very difficult, because these laboratory needs people to work in the laboratory. Work from home is not possible for laboratory integrations and so on. So that has been also quite a difficult thing.
Yeah. So another question, sir. Okay, I will take two more questions now. So we are almost out of time. So one question, like a very simple one, is, sir, do you know which rocket will be used to launch the Aditya?
Yeah. So probably it will be a PSLV. It's a PSLV launch. So far, identified, but they do change sometimes. But so far, what has been informed to us, it will be a PSLV launch.
Yeah. And another question I would take is, one student is asking, like, when the mission is there, what exactly we'll be searching, what exactly we'll be learning from our observation center in ARIES.
Yeah.
So
what are the main objectives people have asked?
Yes.
So as you can see from these 7 payloads, it's a combination of looking at different layers of the atmosphere of the sun. One is, of course, the flare and the CMEs, what we mentioned. When a flare can happen, if a flare happens, then how big the flare is, how much energy is there, what kind of effect it can make. One is doing it post facto. The other is to understand the basic physics of that particular event itself. So, so all the dynamical things which are happening, to understand the dynamical thing, sometimes you need to also understand the static thing as well. See, if you understand the about our normal physical condition, then only you can study the abrupt or abnormal situation. So it's a combination of understanding the solar atmosphere, why the solar atmosphere is layered in different layers, how the temperature is there differently, why the compositions are very different at different heights. See, I didn't talk about it. I mean, there are hydrogen, there are other higher elements in different ionization states. So how to characterize these plasma properties of these different layers, and whatever material is coming from the sun, characterizing the properties of that with the help of these X-ray spectrometers and the magnetometers and particle detectors and so on and so forth. So it's a combination of many things. You can imagine it's a several hundred crore project. So and so many institutions across the country are involved. Majority of the people have different interests and all that. At ARIES, if you say, we are very much interested in the corona and the coronal physics. And the CME studies, how the CMEs propagated in the interplanetary medium, when they can reach and so on and so forth. So the outer atmospheric, properties are of these CMEs, the magnetic clouds, and the plasma properties of the corona and so on are the primary interest at ARIES.
Yeah. Thank you so much, sir. So that was all. I hope students enjoyed interacting with sir. So if you have some few final words before you leave for the students. Yeah.
Okay. Yeah. Thank you again for your time and opportunity. We are all looking forward to the next generation, because I think the future of solar physics in India is very, very bright. I did not talk about the other ground-based telescope from the Himalayan side, which Mila in the introduction mentioned. It's a fantastic location in the Pangong Lake, which we are planning. So a combination of these kind of facilities from space platform and ground platform is a big opportunity. And the other major important thing is just not only from the physics point of view, there are multiple specializations which are involved. As you can see, as I mentioned, for these kind of space missions, so many engineers are involved. I mean, I had to learn so much of, again, some of the engineering element, even, when you say material, the material properties, which material will be good for. So we have to also know that, because otherwise, our observation will get affected if the material is not, stiff enough. So, so the point is, the opportunities are really, really, really good. So I hope, and the lifestyle is slightly different in our area. We are fortunate to be able to carry out our hobbies actually through our profession. So if you enjoy, doing things slightly off track, this is not a bad option. So I will say, get in touch with us, and if you can excite some of the excitement what we have, we'll be happy to do that.
Yeah, I think we, on behalf of STEM&Space, we will try to get some information to them about how to visit, or, you said you're going to be doing training and webinars. So we'll try to keep the information flow ahead to them. Sure. And yeah, it looks great. I mean, somebody asked, why is it high up on a mountain? But, that is part of where telescopes are built, and you've shown such great views, and it's at a great location.
Yeah. Yeah. So normally, we have these local clouds and all that. So if you are in a high up in the mountain, you are not, disturbed by these local cloud formations and so on. So there is something called also boundary layer, which is typically, around 8,000 to 6,000 feet in Indian Himalayan plateau. In terms of the Pangong Lake side, it is even more exciting because it's in a cold desert. So what happens is hardly it rains there. It's a very, very dry place. So in other parts of Himalaya, even in Nainital, we get affected by monsoon. So almost 3-4 months we can't observe. But whereas in the Ladakh region, it hardly rains. So the clear nights clear days are more in number, and high altitude means you are not affected by the low clouds. So that's again a big advantage. So all the big telescopes in the world are actually situated in the highest possible places, whether it is Canary Islands or in Hawaii or in Atacama Mountain in the South America. They're always in the mountainside because of the same reason.
Right. So thank you again for sharing so much knowledge and information about Aditya mission and about solar physics. I hope all the students will be inspired to go into that as a possible career. So thanks for joining us and giving us your valuable time.
Thank you. Thank you.
Thank you so much, sir. So yeah, so thank you so much, student, for joining us. And with this, we are going to end the session.